the refractive power distribution within the treatment zone after ortho-K. And last but not least, we're going to talk about the effect of combined ortho-K and low concentration atropine. This photo comes 30 years ago when I was a grade 2 student, and you don't have to bother looking for me because I'll tell you this is me 30 years ago, and I had 50 classmates, and none of them were myopic. Apparently, here is a girl wearing spectacles, and I can tell you she's high hyperopia. And after 5 years, when we graduated from primary school, we still have 50 students, and none of them become myopic. And still, this poor little girl still wearing spectacles, but she is hyperopic. But none of us become myopic. But this is 30 years later when my son graduated from primary school when he was 12 years old. Look at how many of his classmates has become myopic. 1, 2, 3, 4. Apparently 4 of her classmates are wearing glasses. And I feel very comfortable to tell you a few more are wearing ortho-K lenses. So 1/2 of his classmates were myopic when they graduated from primary school. And you might think that pupils from Yunnan province, which is in the rural West China, the pupils there will have less myopic problems, but this is not the case. When I was in Yunnan last year and I visited there and I do some clinical research and consultation there for half a year, I happened to see a lot of myopic kids there, and we reviewed a reference paper that is published 6 years ago. Um, the prevalence of myopia is shockingly high in some minorities. There's over 70% in some in the Thai ethnicity, and that is over 70%, which is pretty shocking and surprising. But why only humans are becoming myopic? Apparently, those students in Yunnan and their parents received no higher education. They had a lot of outdoor activities, but why do they become myopic? But not the fish, not reptile, not chicks, guinea pigs, or rhesus monkeys, but only humans. And this debate on the etiology of myopia has been going on for centuries. And that is a question of nature versus nurture. The evidence that support the notion or the hypothesis of genes is the ethnicity and the hereditary, because the evidence has shown that the Asians are more likely to become become myopic than the Caucasians, and the children from a myopic family are more likely to become myopic than those that are born in a non-myopic family. And those evidence that is supportive of environmental risk factors, most of them you use in the visual stimuli, and this is my daughter and doing the PowerPoint slides, doing the projects on her laptop, and simultaneously interacting with her teammates on the iPads, which is amazing. This is an interesting and important paper published last year on JAMA Ophthalmology, and the authors have been doing a 5-year longitudinal study to look at the refractive power change in these children and juveniles, and they found that the refractive status remains relatively stable between 2015 and 2019, but it dramatically changed or shifted to the myopic side in 2020. What happened in this year to these kids in this year? Okay, the COVID pandemic lockdown. And during the lockdown just happened, look what skills we have got for our family members. My wife happened to learn to do the bakeries at home, and I learned to do the haircut on my kids, and but I have to give them an iPad for distraction, of course. And my daughter learned to do all the e-learnings and homeworks, of course, the PowerPoint slides projects on the laptop. And all of them all of these activities happen indoors, and you must be not unfamiliar with this scene when our adults have a reunion. The kids do the same thing, and they play video games together. And I give a red background for this to denote that the kids are immersed in a very bad situation where they are experiencing a lot of hyperoptic focus in this environment, which is bad for their refractive development. And here, before I go to ortho K, we talked about a little bit about hyperoptic focus. This the red line outlines the myopic eyes, and compared to emmetropic eyes and hyperopic eyes, the myopic eyes are generally longer and has a prolate and retinal shape. And if we're trying to correct the central refractive error using the single vision lens, we are exposing the peripheral retina to the hyperoptic focus, and which has been proven to be a strong stimuli for research animals to trigger their axial elongation. So what happens after orthocade? Since orthocade flattens the cornea and in the center and steepens the cornea in the mid-periphery, it corrects the central refractive error and brings myopia defocus to the peripheral retina simultaneously. And this is hypothesized to slow axial elongation and do a myopia control with the ortho-K treatment. And this is two papers we published 10 years ago, and to analyze the peripheral defocus after ortho-K. And this is for single vision lens, and that is ortho-K. We see in the periphery, and the refractive status have been changed from hyperopia to myopia. It has been estimated that there are over 2 million ortho-K users in mainland China at this moment, and 75% of of the parents believe that ortho-K has a strong effect on myopia control and axial elongation, and this has been tested in Aerosmith's review in 2013. He he researched a lot of um, excuse me. He looked at a string of ortho-K studies and found that the 2-year axial elongation has been slowed by 40% of ortho-K across all the studies. And that is deemed to be effective by International Myopia Institute, and to be effective for myopia control. But the problem is, for in our clinical practice, our patients had a lot of individual variability in terms of myopia control. I'll give you a few examples for this 7-year-old girl who was first found myopic to be -1 diopter and very short axial length. After 4 years of successful ortho-K treatment, and she progressed to -4.5 diopters in both eyes, and she also had a very significant axial elongation by about 1.8 millimeter. The second case is a 8-year female who had a myopia progression by about 1.5 diopters per year before ortho-K. And when she visited me, she had already -5 diopters of refractive error, and her axial length is already very long. Look, but 4 years later, she had only about between half and 1 diopters of myopia progression and non-significant axial elongation by 0.4 millimeter around 4 years. Look how beautiful the blue eyes is. And the third case is a male, 12 years old, and he had myopia progression about 1 diopter per year before ortho-K treatment. He had -3 diopters or refractive error before orthotic treatment, but 4 years later, he barely had any myopia progression or axial elongation. That is a very beautiful myopia control treatment. So, among these kids, who has the worst myopia control? It is not hard to see that those with a younger age, with lower refractive refraction or refractive error, um, will have um, worse myopia control effect after ortho. Okay, but this the case? We designed a study for 2 years to enroll patients and do the fall zone, fit them with fall zone reverse geometry ortho-K lenses, and they are all of base curve back optical zone diameter of 6 mm, and we use the PanCam tomography to check on the corneal refractive power change and the IOL master on axial length. Basically, we continuously monitor the refractive power in the center all the way to the mid periphery, and that way we happen to have the corneal refractive power change before between the pre-ortho K state and post-ortho K state, and we will add this area together comes a gray area, and we call it summed corneal power change or the cumulative corneal power, and we use this to infer the peripheral retinal defocus change because it's or most of the retinal peripheral defocus is assumed to come from the anterior corneal change during ortho-K treatment. So this makes a lot of sense by measuring the cumulative corneal power change in ortho-K. And what we found is the axial length change is negatively correlated with the cumulative corneal power change and the age. So that is supportive of our hypothesis that axial length is correlated with initial refractive error. So the first question for you is, who is likely to experience fastest axial elongation during ortho-K treatment? Okay, the answer is this one, the fastest, okay, the 8 year with one diopter refractive error will experience fastest axial elongation. Okay, when we come back to the two studies, for our two studies on an ortho-K's effect on peripheral defocus, and we happen to note that most of the defocus change happens on 20 degrees or beyond. But what if the pupil size of this patient is extremely small, that blocks most of the peripheral lights from coming in the eye, from coming in through the pupil margin? Does the ortho-K still effective in this way? And we designed a study to look at the effect of axial growth after ortho-K and the baseline pupil area. We found a negative correlation between the two. And if we stratify the patients into larger than average pupil size and the smaller than average pupil size, we found that those ones with a larger pupil size will experience slower axial elongation than their larger pupil size counterparts. But what if we don't change the pupil size? We might think it the other way. Why don't we change the treatment zone size and make the treatment zone smaller so that we squeeze in most or a lot of the peripheral myopia defocus into the retina through the pupil margin? So the first question is, can the treatment zone size be changed? The answer is yes, because when we design a study to compare different lens designs with different BOZDs, for example, 5 or 6 or 6.2 diameters of back optical zone, we found that when smaller BOZD lenses will bring a faster refractive change and make the most plus power of the plus defocus ring and closer to the visual axis and closer to the pupil center. And those one with the 6 millimeter BOZD, they had a bigger treatment zone size. So this coincide with the Jomapon study published in 2021 when they studied the relationship between the blast power ring diameter and the BOZD, and they found a very significant correlation. So the first question has been answered. The treatment zone size can be changed or can be modified by changing the lens designs. But the next question is, can this treatment zone size if change effectively affect the axial length growth in our ortho-K patients? So this comes from the previous article we just talked about, and they've also found those ones with smaller BOZD are less likely to experience axial elongation, and those with larger BOZDs have faster axial elongation. But there is a significant design flaw in this study because most of the subjects are aged, the average age for the subjects is was 13 years old, which is way too old for a myopia control study. The one that has been published last year by Pauline Cho from the Hong Kong group, they analyzed or they compared the myopia treatment, the axial length growth between the 5 BOZD lenses and the 6 millimeter BOZD lenses, and they happened to find that the axial elongation is slower in the 5 millimeter BOZD group compared with the 6 millimeter group, especially in the first 6 months. After, in the next 6 months, in the second 6 months, there is not significant difference, but cumulatively 5 millimeter BOZD lenses outplays the 6 millimeter BOZD lenses. And this has been evidenced by our earlier experiments on cheeks when I was in Berkeley and Will Sit's lab and doing the check-in works. We found that the location and the ratio of hyperoperative focus, this is a lens for the cheeks that has a -5 diopters in the periphery, and which will bring a hyperoperative focus in the periphery. And when that region becomes larger, the chicken eye is more likely to become myopic. But in contrast, when we use a peripheral myopia focus using a plus lens in the periphery, when we increase this area of +5, the chicken is more likely to become more hyperopic in the end. So we prove in that experiment that the location and ratio of peripheral defocus will affect axial elongation in cheeks. But if that is not persuasive enough for you, and I will introduce you another one that is done in Aerosmith's lab on a rhesus monkeys, and they use this kind of lenses and put them on before monkeys' eyes using unrestricted vision in the center and concentric rings of alternative +3 and 0 powers. And when they the only variation is the first ring eccentricity. Okay, how far is it from the visual axis? And they found that when it's far enough, that it's when it's beyond 20 degrees, they found the refractive status of the rhesus monkey is not different. It's not different from the control group. But when it's very small, the rhesus monkeys will be very hyperopic as expected. So the authors concluded that the defocus might not be effective beyond around 20 degrees of eccentricity. I mean, 20 degrees beyond the fovea. So what does 20-degree mean for an ortho-K kid? Since we don't usually or always measure the peripheral defocus, we will do a model and analyze on the cornea and show you what is the 20-degree means. And apparently this is an axial difference map. And in this difference map, we see a corneal refractive power change before and after ortho-K, and if we take a closer look, we see a very beautiful cone shape and or a spheric treatment zone profile for this kid. And I will show you this is 10 degrees and this is 20 degrees, and this red area is 20 to 30 degrees. And unfortunately, the most plus power appears beyond 20 degrees in Aerosmith's study, and they believe this area is to be not effective for myopia control. So the idea is to how to squeeze this most plus power into 20 degrees, and that is to make the BOZD smaller. And by making a BOZD smaller, as depicted in this topography map, the 5 BOZD lenses yield a much smaller treatment zone than the typical 6mm BOZD lens. And of course, this lens has a lot greater chance by squeezing the most plus power into the pupil margin, and will yield a greater myopia control effect. But how much defocus is needed for myopia control? Is one diopter enough, or three diopters needed, or five diopters sufficient? So in this paper published in 2018, the authors and also look at the refractive power change after orthok and using a Fourier transformation method to analyze the refractive power change, which is very complicated to decipher. But we can look at the results and remember the probability of effective control varies among individuals, with those ones who had over 4.5 diopters in a refractive change. I mean, the maximum refractive power change of the cornea will have over 80% of effective control rate. But that those with only 1.2 diopters of refractive change on the cornea will only have 20% of probability for effective control. So this has been this is an agreement with another study on a dual focal soft contact lenses published in JAMA 2020, and Jeffrey Wallin and his colleagues look at the myopia control effect on the high ADD powered soft contact lenses, the medium ADD powered soft contact lenses, and they found that the higher ADD outplays the medium ADDs in the myopia control effect. So we go back to the this is the corneal refractive power distribution of the previous subject, and we look at the most power and the central plus and the central power. There is a five diopters of difference, but this unfortunately this 5 diopters of difference happened beyond 20 degrees. And the only idea is to not only to make it smaller, but also to make it more aspheric. And we go back to the previous study that we published earlier this year. The 5mm BOZD lenses tend to yield a more aspheric zone, which depicts a faster refractive change profile in 5mm BOZD lenses as compared to the 6mm counterparts, both in 1 day, 1 week, 2 week, and after 1 month. They are still different. So this is a cone-shaped pan which depicts a more aspheric treatment zone, and this is a flat pan which depicts a more spherical treatment zone. But the question is how to analyze these shapes, the asphericity, in a mathematical way. In a study we published earlier this year on TVST, we found an equation. This y equals x exponent n to this monomial function to depict the relative corneal refractive power change after orthok. Sorry, with a smaller n, with a smaller power exponent, depicts a faster refractive change within the treatment zone and more asphericity. And the larger means a slower refractive change within the treatment zone and less asphericity. So when we designed a study that lasts for 1 year, and in that study, we all the subjects were treated with the Peregrine CRT lenses of a typical 6 mm BOZDs. And we used the minimum topography to check on the corneal power change and the IOL master on axial length. And we try to analyze the effect of treatment zone size and sphericity on axial length growth. We found that the children who had more sphericity in the treatment zone will have much slower axial elongation after 1 year, and those with less aspheric zone treatment zone, that is a flat pan treatment zone, will have faster axial elongation. If this study enrolling the Peregrine CRT lenses is not persuasive enough, then this study should be considered. And in this study, we enrolled more subjects, about 137. We used three lens designs, the DRL, which stands for the double reservoir lens, the Euclid, and the CRT lenses. They are of 6 mm, of 5 mm, 6 mm, and 6.2 mm optical zones. And by the methodology resembles the previous one. And this graph shows us the relative corneal refractive power change profile within the treatment zone after the treatment using different lens designs. The red one stands for the DRL, and Euclid and one for CR. And it's not a lab. And we found the exponent or the sphericity of the DRL lenses. The power exponent is the smallest, and in the CRT lens is the greatest. And agreed with this finding is that the myopia control effect also varies among lens designs too. The DRL lenses, the subjects happen to have the slowest axial elongation after 1 year. It's slower than 0.1 millimeter, which is pretty slow. For Euclid lenses, the CRT lenses, after 1 year, the axial elongation is between 0.26 and 0.32 millimeters in average. And and by comparing the treatment size and sphericity and age effect on axial elongation, we found that the sphericity of the treatment zone is the most reasonable predictor for myopia control after ortho-K treatment. So the second question for you is that which pattern of treatment zone is best for myopia control in ortho-K? The answer is the first one, a small and a spheric treatment zone. Okay, for those who are familiar with our studies, must know we have done lots of studies by using ortho-K and atropine. So how do we help those fast progressors? How do we define the fast progressors? In our study, we define the fast progressors to be those who had undergone ortho-K for 1 year but still had 0.3 millimeter per year of axial elongation, and they are all under 12 years old. Um, for these kids, after 1 year, we add 1 drop of 0.01 atropine eye drops per night and compare the axial elongation rate before and after atropine use. We also included a historical control group who are ortho-K patients only using ortho-K treatment for 2 years but no atropine at all. In total, we enrolled 60 subjects, and here's the biometric data. For phase 1, we're using ortho-K only, but for phase 2, we're using a combined treatment for the test group, but for the control group, they continue to use ortho-K but without atropine use. With the dashed line here stands for the control group, and the solid line here stands for the experimental group. for the experimental group, all of them are fast map progressors, and it progress at an average of 0.45 millimeter per year, which is pretty fast. And at the end of 1 year or the beginning of the second year, we start atropine combination treatment. And after the add of atropine, the axial elongation rate slows down dramatically to 0.16 millimeter per year. And this can be partly due to the cycloplegic effect of the uh, of the of atropine, 0.01 atropine has been tested in the atom studies to have a pupil effect to but 1.2 millimeter becomes larger. And this bar graph again shows us the comparison between before orthok and after orthok. Sorry, before orthok and after orthok, which is pretty significant. And one might argue that the baseline axial elongation rate differs between the experimental group and the control group. So we did a 3 year study to see whether the combination effect of orthok and atropine can last beyond 2 years. So we enrolled another group of patients, and all of them had been undergone for orthok for 1 year, and still all of them are fast progressors at over 0.2 millimeter per year, even with orthok treatment. And for phase 1, we use all the orthok, and for phase 2, we use in atropine, but this time we're using for 2 years. Okay, for these cases, the biometrics basically resemble that of the previous one, but the difference is that in phase 1 we're using orthok for 1 year, but the phase 2 we're using atropine in combination with orthok for another 2 years. Okay, by adding orthok, it dramatically slows down axial elongation in those fast progressors, but the third year does not significantly varies from the second year. So the effect of the map control effect does not seem to be cumulative in the atropine group. But in the orthok group without atropine use, the axial elongation slows down over time, probably due to their aging effect. But in a total of 3 years, the OK group does not vary significantly from the OKA group. And in this line chart is more obviously to see that the solid line stands for the experimental group, and here, when atropine is added, it slows down dramatically, but not until 1 year later it becomes parallel to the control group, which means there is no more effective atropine in this case. This the you know the OKA group is done. The OKA study has been done in a few studies, and this one is published in a Japan group, the Kinoshida's group. They have been randomized the subjects to orthok and OKA group. So the combination group here is the solid line, and for it is evidenced by the first year that the OKA group progressed much slower than the OK group, but for the second year, we didn't see a very significant difference around here. And another one in Pauline Cho's study, they also randomized the subjects into OK group and AOK group. So the combination group happened to have a much slower axial elongation during the first 6 months, but in the second 6 months, those two groups paralleled each other. So we didn't see a cumulative effect of AOK group compared to the OK control group. Okay, here are the part of the references I cited in my speech today, which is published by our own team. And thank you again for listening. And per the request from the committee, I propose two multiple choice questions for you. The first one is, if an 8-year-old patient undergoing orthok treatment had axial elongation of 0.6 millimeter in the last year, what should you do? Would you wait and see? Would you update prescription without changing lens design? Would you try a different orthok lens design? Or you try to add low concentration atropine eye drop? Please note this is a multiple choice question. And the second question is for me. What do you think of this course? Is it easy, normal, or difficult? Is it helpful or not helpful? And could you please provide your feedback to peter459 at aliyun.com. And if you have any questions on my studies or on this speech, please feel free to contact me. Thank you very much for listening.
Able to hear me now? Okay, thank you so much. Okay, I was saying that thank you everyone for being patient with us just now when we had the issue with the video. Now we'll start our third poll for the day before our final presentation. So our third poll for the day is, which aircraft has the biggest